Thank you very much. So I saw the idea to have a coffee break just after me is because you'll be enduring such an effort during this hour that then you really need some coffee to be able to continue. Well, apart the colors that are very winter-like for a winter school, I think is appropriate. I think that, I mean, what you're going to hear during this hour is a kind of broad mixture of things that go from a machine, so accelerator issues, all the way to the interpretation of the data. And, I mean, the value here, I mean, I've been looking a little bit what else you have been hearing during this school. This is going to be very different. However, I mean, the LHC has two great points of strength. The one is that it really exists. I mean, it's something very physical. You have no opportunity to go down in the tunnel, but it's a reality. It's a physical reality. And second, it is, and even more will be, I mean, through Run 2 and Run 3 and possibly the iGloomy upgrade, really the point of reference for whatever ideas you can have. The most natural thing will be to go and see if the LHC data tells something that can guide you in further working out your theory, falsifying it, or proving that maybe there is some phenomenology that actually is seen or can be seen. And then I'm going to try to point out in my talk, the LHC data doesn't come as a single piece. The LHC data is built by the a priori ideas that we have, you have about physics. The LHC data is not just given to you on a tape. Whatever happens in the collisions is not delivered. The LHC data goes through filters, which are triggers, which are data analysis streams, each of which is recorded because you have some idea, some a priori intuition that new physics or interesting physics may have a given signature. So it is extremely important that if you have any concept of how your theory, how your model may be realized in a phenomenological way, you do speak up. Because unless that specific phenomenology is represented somehow in the trigger menus of the experiment, or you take the risk that that specific physics will never be logged on the tapes, so will never appear afterwards. So while, I mean, in the plus and minus collisions, whatever happens is recorded, and even today you can go and look at all the interaction, plus and minus interaction events that were recorded at LEP. The LHC data is only recorded the part of the statistics which the experiment have decided is interesting. So it's up to you through the next decade, when you make the transition from sitting there to standing here, I mean, to actually speak up and say what is interesting. So this definition of interesting is really what motivates to have a very strong, a very tight connection between theorists and experimentalists. And this, I think, is really a major red ribbon leitmotif through my talk. So just to get started, I mean, we've been both in Europe and in the US through a very lengthy and interesting process of review of what particle physics should be in the next decade. It's been obvious that the exploitation of the LHC to its full capabilities is really the Europe top priority in hydrogen physics. And the full capability of the LHC includes a long-term upgrade to high luminosity of both the accelerator complex and the detectors. I mean, this part will not be represented very much in my talk because the organizer has put this Run 2 status and perspective, so I will try to concentrate here on what are the perspective of the machine as it configured currently in the tunnel. But the LHC program is something that is going to span through the through the first third of our century. So it's extremely important. So it's something that is not easier, but is here to stay for a long time. And the Higgs boson discovery has actually opened up a very broad and engaging program of studies, of measurements, actually to understand the role of this new particle compared to the standard model. And the main question that we are all putting to ourselves is this a Higgs boson of the standard model, or is something else? So this is a first manifestation of some new physics. And also, I mean, in the connection with cosmology through dark matter. I mean, the Higgs boson has most probably some relation with dark matter, as dark matter is due to a weakly interacting massive particle. And that's something that the LHC program is now called in to elucidate. So the program includes both direct searches, what I was meaning, I mean, go out and look if there is something that deviates from distributions that are predicting the standard model, but also precision measurements, as the Higgs profile is part of that, measures the Higgs properties with very high accuracy, and so this will allow to extend the mass reach, both through the energy increase. We went from the run 1 that was between 7 and then 8 TeV, to run 2 and run 3 from 13 to 14 TeV. The luminosity, we have collected about 25 inverse femtobarn so far. We'll get to 300 inverse femtobarn, summing up run 2 and run 3, and we'll go to 3,000 inverse femtobarn through the projected high luminosity. So you see that we are talking several orders of magnitudes of increase of our data set. And so this is what allows, I mean, to push all the sensitivity in mass and in towards rare decays. So the upcoming LHC Run will generate some unprecedented corpus of data that will become probably the standard test for whatever new models or a new theory that you may be interested to see if it actually is realized in nature. So there has been a long shutdown 1, been going through, I mean, a very lengthy work of consolidation of the machine and the preparation of the machine to operate at its design energy of 7 TeV per beam. I mean, this program is now finished. The machine is now ready for a commissioning. We'll go through the schedule in a moment. The 2015 run will have different configuration of the beams. And you see that will give an expected luminosity between 5 and 9 to the 33. I mean, we'll be going closer to the 10 to the 34 design luminosity for the machine. The run 1 has been running with peak luminosities of the order of 6.5 to 7 to the 10 to the 33. Here is provided, combining the 7 plus 8 TeV, 25 inverse femtobarn of data, that even though seems small compared to 300 or 3000, this has actually brought in the standard model rediscovery. When I say the standard model rediscovery, I mean going through all the standard model processes, which measurement of W mass as a top mass, has brought in the Higgs boson discovery. That will be up to you to decide if this is part of the standard model discovery or not. And I mean, a large number of searches for new physics, on which I mean I will spend some time. Now we are sitting somewhere here in February. So the machine is now restarting its new life, powering test, checkout, beams will come in sometime at the end of March, and with the beginning of June, there will be the first physics. And so this will be the start of the physics run of the LHC. So that's something that's going to come quite soon. So the program for that will be the region, these 2 years here, will be to ramp up the luminosity, I mean up to 10 to the 34, which is a nominal luminosity, operating in 2015 at 13 TeV, and then depending on the performance of the machine, I mean going to the design energy of 14 TeV. Run 1, which will run until 2017, will give you between 100 and 120 femtobarn inverse, which is already a factor 4 to 5, larger than what we have on tape today, so it's a significant increase. You have here, typically due to the energy increase, something between factor 2.5 to 5 improvement in the cross-section, and then you have another factor 5 here improvement in the data set. So that's already, I mean, a factor about 20-25 improvement in what you can use your LHC data to test. Then up to 2022 will be about 300 femtobarn collected at 14 TeV. To go then through a long shutdown, installing all the crucial components to make the final jump in luminosity, and then go up to a factor 5 to 10 to 7 higher luminosity that will allow it to get by 2035 about 3 inverse attobarn. Of course, I mean, through all these programs, there may be hopefully there will be discoveries, there will be new data, and so new knowledge acquired, and so the program will naturally adapt to whatever will be seen. And so then this is our view of today. This is certainly a very dynamic program, and so this will naturally be adapted to what will be observed. We'll learn what will be needed. So physics event and reconstruction, I mean, from the machine, I mean, to get some plots that tell you if there is excess of events beyond the standard model. It takes a very long process. It's something that usually is done by the experimentalists, but I think it's relevant that for maybe about 15 to 20 minutes we discuss that together, because it has a significant inference on how then you can use the LHC final results for theory testing. So the main observation when you are looking to the proton-proton cross-sections as the energies of interest is the fact that there are typically 7 to 10 order of magnitude between the total cross-section, interaction cross-section, and the typical cross-sections of interest for the processes that you want to look for. So there is this mismatch of needs to be addressed by applying, I mean, some very strict data selection, and this is the main challenge that an hadronic machine of the energy of LHC, I mean, is facing. So what you do, I mean, you tend to reconstruct, you want to reconstruct all your physics objects from the response of your detectors, and I will not go in any details there, but basically the output of the experimental activities analyzing the data collected from the detector is to give you, I mean, the photon, electron, neutron, pions, muons, jets, missing ET, secondary vertices, all these physics objects that has been reconstructed in a single event, and then it is up to you, phenomenology and experimental activity, to go from these individual particles, which are constructed in the detector, to the event variables which characterize and discriminate between standard model processes, signal processes, new physics processes. And this is a process that requires a lot of ingenuity, because if you have to overcome 7 to 10 orders of magnitude in cross-section, I mean, this needs to be done in a way that is extremely effective in rejecting the part of the cross-section are not interested while maintaining some significant efficiency. In addition, I mean, you're running a machine, and what you want to maximize is your luminosity, because the number of events that you'll be seeing in your detector are basically the product of the signal cross-section times the luminosity. But since you are operating a machine where the luminosity is achieved thanks to a large number of bunches and a large repetition rate, the number of events that you have for each crossing of the beam bunches also scales as a sigma times L, where the sigma here is not the interesting sigma, but is a total cross-section. And so what happens is that in a single bunch crossing, in a single snapshot, you can take of what is happening at the interaction region, you have a large number of minimum bias events which are generated. I mean, in the case here, there are something like 78 minimum bias in proton-proton in elastic processes which are happening. And there is no even certainly no new physics. There is no IPT standard model physics going on in this event. So these events, of course, they deposit energies, they generate particles, they do generate extra physics objects which are not related to the IPT physics you are interested to detect and to study. And so you need to deal with them during the event reconstruction. The first thing that you have as an advantage that the long bunch length spreads actually this event along the beam axis. So you can already start discriminating them because each of these events happen in a different position longitudinally along the beam. At the S7 TV, the inelastic cross-section was about 85 millibarn, and it will be 105 millibarn at 14 TV. You're talking here about 100 millibarn when typically your signal cross-section is the order of between the picobarn and the femtobarn. So you see the issue here. When you look to this effect of this overlapping event, this event pileup in your detector, and you look in the case, for example, here you have TT bar production with lepton plus jets in the final state. If you had no overlapping event, I mean your transverse energy, missing energy, will be basically is due to the neutrino originating from the W from the top decay, will going around the orange curve here. However, depending if you have 50 of them, 140 of them, which is a typical number that you expect between run 2, run 3, and the luminosity run, you see that this distribution gets a very significant change. Of course, this is a problem for your reconstruction because exactly the deformation of these distributions are the signature for the new physics that you expect to bring in extra missing energy, for example, compared to the standard model. So it's important on one end to suppress the effect of the event pileup, and on the other end to measure that very accurately. So there are a number of ways that you can topologically try to disregard particles which are coming from the pileup events compared to those that are coming from the main IPT physics process. To give you some simulation where here is a function as a number of pileup events. If you have basically no correction, you see that, for example, your resolution on the missing energy will degrade linearly with as many events you pile up into your detector. But then, you can suppress them, through the event reconstruction until you can tend to flatten this. And so this is a way that then you can afford to have some significant pileup. Something similar happens here. This is instead, a different curve are obtained for a different number of pileup events between 40 and 140. This is typically what will be about in run 2. This is what will be about in the high luminosity run. And you can see this is sum of the transverse energy in the event. And you see that, this tends to remain rather flat. So, but these are major issues that also make some limitation to the luminosity. You are not operating the machine at its full potential in terms of luminosity. You are operating in a regime which maximizes the benefit of the luminosity that you take into account the experimental condition that you have in your detector. Another part of the effect of having such a large total cross-section is the fact that, you need to pre-select your events because, typically you have triggers, so you have a rate of events which are coming in, which are essentially the beam crossing, so 20 to 40 megahertz. There is no way that you can handle the data from your detector and put it in storage at this rate. So you need to have some logic which down-selects events based on criteria that you have defined that say what is interesting, which reduces through hardware and software stages down to order of 100 Hertz. So you have the typical event rate, if you take only the inelastic process, is about 10 to the 9 Hertz. And then as a typical rate for the processes of interest is oscillator between a fraction of a hertz and maybe 10 hertz. And so you need here, you have the same 10 to the 7, 10 to the 8, 10 to the 9 factor that you need to reduce your data. And so after you've done that, you can do that by still keeping, highlighting some kinematic regions. This is, for example, proton-proton in mu-mu. So you see that especially select your triggers in such a way in which you keep more of the regions where there are resonances of interest, but then you tend to suppress the rate to keep it manageable. Still, when you do that, the LHC becomes a major player in the big data world. This is a plot that was made for the CHEP conference last year. So this is a plot that I wanted to show to you. So this is the kind of data sets that we are dealing. So the LHC data is about 15 petabytes per year that is collected. This is basically comparable to the uploads on YouTube. This is much larger than the Library of the Congress. Knowledge that is stored. If you take, all the current Atlas data sets, including simulation and everything that has been stored, this is 140 petabytes. This is about as much as you have through the Google searches. Is about what you upload on Facebook in 1 year. So LHC, even with this reduction of 7 orders of magnitude through the trigger, is still a major player in the big data world. You have, of course, different ways in which you can handle your data. So you typically have experiments like ALICE, the heavy-ion experiment on the LHC, that has inherently a very large data size because the multiplicity of their event is very large. And so then in that case, you need to run at a very low level 1 trigger rate because your events are large. And so typically here you'll push through a very, very large data set at a low rate. Experiment like LHCb, that is the dedicated B-physics experiment on the LHC, has a very small data size because the events are small. The amount of particles produced is very small, but they are looking for rare decays, so you go actually on the other axis. Here you have a small event size, and you can push through a very large event rate. So since you decide yourself the trigger, there is a lot of flexibility in deciding where to go. The multi-purpose experiment, Atlas and CMS, they have none of these two. They have a very large events and very large rate. So then they have to stay somewhere on the diagonal here and decide themselves what's the best way to use the available throughput of data. So the trigger selection and the hadronic background, as I say, make very imperative to define some well-defined signature for the kind of event that you want to see. So these are signal topologies. So there is theories, there are models. Whatever you want to probe as the LHC depend on a large enough number of parameters, and the way that the signal looks like depends very much as you move on this parameter space. So you have to be alert that you don't miss regions of the parameter space of your theory because the signal topology changes as the parameters do change. So the search topologies are driven mostly by physics, but also by the triggers that you have available. The physics object that you can reconstruct, lepton, photon, jets, missing ET, B jets, whatever. And so, for example, you want to say, well, I want to see anything that may produce resonances in dijets, dilepton, diphotons. This is a typical event I have here. 2 muons in my event. The invariant mass of these 2 muons makes a resonance, which may be signal of some new physics. You can look for jets, lepton, photons plus missing ET, for example. That's typical what you do in supersymmetry. You can I want to look at B jets, anything that goes into Bs and not into light jets, and then you go identify my Bs. How many B jets I have in my event? I can look in multi-jets. It was something that was done in the early times of the LHC when people are thinking of black holes being produced and evaporating in multi-jets. People were looking into 15, 20 jets in the detector, something like that. So all these physics signatures are somehow connected with dedicated triggers that the experiment has and to the dedicated searches. So it's up to you to find out, once you have an idea about new physics, where does it shows up in these different categories? Does it in any? Does it in many? Do you need to introduce one new? So there is another aspect that is very interesting. The LHC searches are not performed by physics theory, are performed by topology. So once you have a search done in a given signal topology, the result that you have obtained can be reinterpreted in another physics theory if this results in a similar topology. And so this is very interesting. Sometimes you can reinterpret a SUSY search into a completely different context. For example, you can interpret a SUSY analysis in the context of universal extra dimensions, because both of them will be characterized by generation of standard model particle plus missing energy. So whenever you are developing your theory or your model, it's important that you ask yourself whether the LHC may already or will have something to do, something to say about it. Just to give you an idea, I show you, this is a SUSY search performed by CMS in 2013. The way this search is performed is by looking topology. So for example, the analysis here, we're looking at the multiplicity of jets containing a big quark as a function of the total jet multiplicity. And so it was characterized here in terms of standard model background and with some signal on top. So each of these categories was individually studied, and you could measure how many events you're observing in each of these sets compared to how many the standard model predicted. SUSY, in this specific case, would have shown up in some regions, but also some completely different physics may show up in the similar regions and then be reinterpreted. At the same time, people were looking at the transverse energy, some transverse energy of the event as a function of the missing transverse energy of the event. So we're looking here in signal regions and standard model control regions. So SUSY was expecting to show up in some of the regions up here, but the same that corresponded to some of these specific jet hadronic topologies. But that doesn't need to be only SUSY. Other theory could also show up there, and could therefore this data be used for testing them. This is because at the end of the day, once an analysis is performed, the net result of the analysis is either a Nobel Prize, because you discover the Higgs boson, or in most of the cases, is a set of upper limits or measurements of the cross-section for a process times some branching fractions times an experimental map which gives you the efficiency times acceptance for that specific piece of the kinematic space. So what the experiment tells you is if you do a certain analysis, in this case here is a mass, this is a case of SUSY analysis, but as function of the masses, but you have the same as a function of kinematic variables, which is efficiency times acceptance. And note that because of the high rejection that you want to have on the standard model background, these numbers here are not in the 50, 70%, they are in the few percent. So typically your analysis efficiency is also a few percent on the signal, because it needs to have several orders of magnitude rejection on anything else. So what you can do, I mean, you can start from the LHC cross-section upper limits, which are produced from the experiments. You can generate your completely new process that is the manifestation of your theory. And then you can go and get the efficiency times acceptance matrix of the trigger selection of the experiment, of the selection cuts. And this you can do because the experiment gives you enough information that you can actually do that. And then with that, you take the result of the experiment, you replace the acceptance matrix of the experiment with the one for your specific model or theory, and then you extract the upper limit for this new process. So there is a lot of this which actually is being done by theorists in the interpretation, and there is support by the experiment in doing that. So we're going towards the physics. I will just highlight a few parts. Last year I spent quite some time about the standard model rediscovery. I mean, this has been rediscovered, so this time I will concentrate mostly on WIMPs and the Higgs sector. This is one of the Higgs candidates. So what the LHC can do, I mean, in going and looking for new particles, especially those which may be connected with dark matter, with weakly interacting massive particles, and so, is to go and look per production of those through whatever process originated by proton-proton collisions. So basically, in all the plots that I'm going to show, you see it inside this big blob, in the sense that that's where the interesting physics happens. But when you're looking at it, you stay out of the blob. Whatever has happened here it can be an S-channel, can be a loop process, can be a box, whatever happens inside here. You stay out here and you'll see the production of some new particles. And you see these new particles eventually going into standard model particles, maybe plus something that escapes the detector. In the case, this is the case here, is the production of squarks or gluinos in pairs. You have already, with the current data, this is not run 2, this is run 1, what we have already on tape, you have constraints which go up typically on mass scales, so about a TV for some of the processes. You see here, the observed here going 150 GeV. I mean, it goes up to a bit more than 1 TeV here under some conditions, and there are large parts of the parameter space which actually are left unprobed. But I mean, as you push them, I mean, to the limit, there are already the capability to test up, let's say, the TV scale. If you ask yourself how this is going to evolve, in this case, there is a simulation of Gluino production in SUSY, in the MSSM. I mean, if you throw a large number of models, this is a distribution of the Gluino mass that comes out. The distribution here shows basically what is left untouched after the run 1. So basically, I mean, anything above, a little bit below, about 900 GeV, I mean, is been probed, or mostly probed. What is above, not. The run 2 plus 3, I mean, will probe essentially up to about 1.9 TeV. The luminosity LHC will probe beyond 2 TeV to about, I mean, 2.3, 2.4 TeV. This is also shown in the experimental plot. I mean, these are projections from the experiment. They show something similar. I mean, currently here you have your reach up to a bit above 1 TeV, but with large holes. And then, I mean, as you are going up to 300 femtobarn, and then you go up, which is a line here, you go just a bit above 2 TeV as a maximum, but you leave some regions unprobed, and then you go essentially up to almost 3 TeV with a large luminosity. So you see that luminosity and energy and mass scale are, of course, have a large trade-off. So you can push your sensitivity by increasing the luminosity, so probing the tail, your Parton distribution function. So this is very important. It's different from the lepton colliders. In the hadron collider, actually, luminosity corresponds to an energy increase, an energy sensitivity increase. If you're looking to, for example, scalar tops, again, here the complexity of event increases. There are more standard model particles in your final state here. You see again that you have some coverage up to something like 600 GeV, but with large holes. This is CMS, this is Atlas, so you see this is very similar. It is interesting to look also to weak production. I mean, these are all strong production processes, but you can have weak production of new particles. I mean, cross-section are correspondingly lower. But here you are now probing really in the core of the piece of the theory, which may be connected to dark matter. These are the neutralino in SUSY, one of the leading candidates as a WIMP. So you see that you already have some sensitivity which is significant. You see that in principle you can reach out to something which is not far from the kind of limits that were for the strongly interacting particles under some conditions, but you can already probe up to 500, 600 GeV for both experiments, 700 GeV in some extreme case here. When you'll be going to 300 femtobarn or 3000 femtobarn, you see that your reach will go basically closer to 1 TeV in all these cases. So it's also to show that it's not true that a proton machine is only good to see strongly interacting particles. It's very good to see also weakly interacting particles, provided that your luminosity is large enough that actually you can get this sample. And this is an exemplification of that. I mean, so you ask yourself, I mean, what's the relevance of this number? I mean, and when you turn to the WIMP dark matter paradigm, we've been living, I mean, through the idea of the WIMP miracle. So the fact that if you have a weakly interacting massive particle with a typical cross-section corresponding to weak processes, you get naturally the dark matter of relic density measured by the cosmic microwave background with a mass which is above about 100 GeV. However, when you do that in a specific theory, like for example in supersymmetry, you find that the situation is a bit different. So it goes from the order of magnitude study to a detailed. So you see here that this is the 0.1 in relic density corresponding to the Planck result. I mean, this is obtained basically for different choices of the nature of the neutralino and the neutralino sector mixing matrix with anything that goes exactly between 100 GeV all the way up to 3 TeV. So there is in a well-defined theory where more particles can contribute to the annihilation processes, to the production processes, you have a very broad range of possibilities, and this is a corresponding result that you have for direct detection. So having this probe that goes to a TeV or even beyond is extremely important because, at least within SUSY, the TeV is a natural mass at which you may expect a WIMP to sit if this is responsible for dark matter. You can also do something similar, but doing some abstraction from a well-defined theory and do that in effective field theories. And so there, I mean, is interesting because the LHC can perform searches not only looking for well-defined final states which correspond to a model which predicts production and decay of your particle, but can do it more in general. You may look again to a blob, where again you'll sit in this blob and tell us what is actually the physics which happens inside here, or you don't tell if you don't know, and you do an effective theory inside the blob. And I mean, you look to the radiation of a gluon, a photon, a W, Z, something out of the incoming leg here, which is basically witnessing the fact that you have a hard scattering processes. So you are looking for events in which you don't care what your dark matter production process is, but you're looking for events where there is nothing in the detector except something that tells that actually an interaction has taken place. And so this is a smoking gun that something has happened. So this is interesting because the sensitivity of the LHC data then it can be estimated either in the framework of full models like SUSY or of effective field theories. So here, typically, you can interpret your results as the ratio of a mass scale, which is a mass scale of your theory, divided by some coupling constant. And you can relate the limit, which are typically put on these ratios, to the value of the scattering cross-section of this particle on nucleons, which is obtained by dark matter direct detection experiments, which are typically looking for the faint signal of a WIMP which scatters off a nucleon inside a large volume detector underground. And these are the scattering cross-section depends again on your mass here and of your couplings here. So these are basically, we are working exactly in the same base because the scattering process is just the same diagram here, but just inverted. And there has been a lot of work that has been done recently on that. You do have such events. I mean, there is one in the Atlas data, so this will be an event where you have just a lonely jet in the event and nothing else. I mean, it's very striking when you see that. So there has been searches performed in the monojet, so single jet produced. You have here distributions. You see that new physics will show up in a far tail of the transverse energy associated to the single jet. In here, instead, the data seems to follow very well the standard model background expectation. You can do the same in the monophoton. You use a photon instead of a jet as a probe for the R process. Again, here you see that there is a very good agreement, where there is even some deficit in the data in the Higgs transverse momentum. You can do where you use a Z, for example, the boson radiated off. And again, here there is agreement, while you'll expect in all these cases excesses as you go to large missing ET. But that's something that is happening now, and this will continue to happen. So these are very simple topologies. It depends very little on what the model is. So it's a powerful probe. This is, if you take effective field theory, this is one of the gluonic real operators, just one out of some work doing with a number of friends, series friends. So you see here, so this is your mass of your effective theory. This is a mass of the WIMP. So this is a region which is actually, that would be probed by 300 by femtobarn of 14 TeV data. So all the region down here will be excluded. You see this line here shows a region which is compatible with the Rayleigh density, that is this funnel that goes in here. So this region will be probed, and this is a region that is probed by the direct detection data. So you see that if you put together all that, I mean the direct detection data, LHC data, dark matter direct detection, you can get, you can basically over-constrain, I mean, some of the region of this parameter space. This is the same where you can now project the regional sensitivity of the LHC on the plot where you show the scattering cross-section for WIMP direct detection as a function for the mass of the WIMP itself. So you see that there is a very strong synergy between experiment directly looking for dark matter and the LHC searches, which will be probably one of the highlights of the upcoming run, because both LHC and the direct detection experiments will get a significantly leap forward in sensitivity. You can also look to monojets in context of supersymmetry or a well-defined model, for example. And then what happens there is that you go and probe regions which are difficult for the direct search. So here you're probing the region of large mass degeneracy, for example, where monojets have a large sensitivity. This is exactly where your direct detection becomes weaker. So again, monojets can be used in a well-defined model and go and cover some specific region of the phase space. It's interesting that the accuracy that you can get with the Gluino searches LHC is not only a number. As you say, this number was 1 TeV, becomes 1.5, 2 TeV, the larger the better. This actually can become very interesting in a quantitative term. I mean, this is, for example, if you take in the context of Gravitino dark matter, and you are going and look at the regions of your parameter space where you are plotting here the Gravitino mass as a function of the Gluino mass, there are regions which are allowed basically above these curves, depending on the radiating temperature of the universe. Now it's interesting because the radiating temperature, the inflation, depends as some tight constraint which come from cosmological bounds. And so typically you like the temperature to be quite large, let's say in the order probably 3 × 10⁹ GeV or so. And so in case you don't observe any Gluino as the LHC at 14 TeV and even more in the gloomy LHC, then you can fully exclude this region as a parameter space. So basically you can exclude radiating temperature in Gravitino dark matter models basically that are the value best fitting with leptogenesis scenario. So you can bring in data on supersymmetry and connect that with data on cosmology and try to over-constrain some parameter regions. And in some specific models, and this is one of the specific models, you can actually obtain some exclusions of all the available parameter space. So this is the value of pushing as much as you can through the higher luminosity your probe or the mass scale of new physics. At some point you come and you totally cover some parameter space.
Sorry, what is the capital and little g? Is it the couplings?
No, this is a Gluino mass and this is a Gravitino mass. I forgot I tilde on top.
I didn't understand the difference between capital G and little g.
Yeah. So this is a mass of the Gluino.
Yes.
And this is a mass of the Gravitino in your model. Yeah.
As a function of?
Or the Gluino mass.
Gluino mass,
yeah. Here you are in a SUSY scenario, but this is a SUSY scenario, yeah, this is a pattern of the gluon. This is a SUSY scenario in which the lightest particle is not a neutralino, but is a Gravitino, specifically. The Gravitino, which is a partner of the Gravitino. So Higgs physics and the LHC, last 10 minutes probably, but I mean, can't avoid discussing that. So, well, you know everything about Higgs production as LHC, but I mean, I can't avoid to show it to you and to remind you that even though the discovery of the Higgs had a lot of input by a single process, gluon-gluon fusion, which has the largest cross-section, there are a number of different processes which lead you to the production of the Higgs in proton-proton collisions. And I mean, the cross-sections are given here. At NLO, I mean, you see the gluon-gluon is by far the largest, but WW-ZZ fusion, TT fusion, associated production are important, first because they give you access to Higgs couplings, TTH, WH, ZH, and also because they allow you to see final states, which will not be obvious to see in this case. So, for example, if you look into two-photon final state, two photons have very small standard QCD background. So this was observed actually mostly through the gluon-gluon fusion process. But if you want to look at the BB bar process, BB bar has a huge QCD background. So the best chance you have is to look at in associated production with the gauge boson, which basically tags your electroweak process and rejects QCD background. The use of the experimental data is not full until we don't understand the underlying theory uncertainties. And there are three groups of theory uncertainty which definitely need to be addressed. The first one, I mean, is a theory uncertainty on the production cross-section. So, I mean, whatever you measure always the product of a production cross-section times a decay branching ratio times some luminosity. So if you want to go and study the coupling of your particle, which are responsible for a given process, you must know which is the production cross-section. Whatever uncertainty of there propagates then linearly to your accuracy on the coupling. And you see here that, I mean, there are still very sizable, I mean, if you take 14 TeV, even taking the NNLO calculation for the gluon-gluon Higgs production, there are very sizable uncertainty of about 10% from the scale, another 9% from particle distribution function at alpha S, another 7% from the effective field theory that you are using. So unless you can beat down all these uncertainties, or there will be little advantage to beat down a lot of experimental accuracy, because at the end you'll sum them in quadrature, and at some point these will become dominant. So it's extremely important that the theory community can come in and help and reduce this uncertainty. Then there is the fact that, I mean, when you interpret the Higgs sector, you want to have good control of the quark masses. You want to have good control of the B mass, for example, when you want to study the coupling to the B, which is still, I mean, has uncertainties which are very sizable, even from lattice QCD. Not only they are sizable, they are also not well understood at the moment. If you take the top mass measurement, now you have accuracy which is falling below 1 GeV, and so you have to ask really yourself which mass are you measuring, and which is a relation of the mass which appears in the theory expression and the mass which you are measured when you extract a kinematic distribution from some simulation of your events. So you are doing fit to the invariant mass of the jet. Effectively, you don't measure the ms bar mass. You're measuring some kind of generator mass and PCA mass. And so then, I mean, you have to relate that with a mass which is relevant to do your experimental, so your theory calculation. So it's important, I mean, to make this connection as reliable as possible, or to give instructions how to extract the masses from the experimental data, which is basically kinematics that is available, to get full profit of the top mass accuracy from the LHC measurement when you want to reinterpret in the Higgs sector. What you measure typically is a product of a production cross-section, as I mentioned, with a sizable uncertainty times branching ratio. You measure that typically you quote them normalized to the standard model prediction in what you call a signal strength. 1 means a particle behaves exactly like the standard model, different from 1, then is exciting. How much excitement is around? Well, you see the number that are measured by the two experiments, dB bar, tau tau, gamma gamma, WW, ZZ. The reasonable lineup on 1. So this is what we call a standard model like Higgs. Something similar for Atlas, so a little bit of fluctuation on the dB bar. There has been the LHC, I mean, is always a discovery. It's not only a discovery machine for finding new power, but it's discovery for doing things that it was not expected to do. There has been an attempt by CMS to measure the total width of the Higgs, something that was not expected to be actually doable in proton-proton collision. So that's interesting. I mean, the amount of data that comes out is interesting. There is a fundamental test for Fermion and Boson mass generation. If you plot the coupling of the particle to the Higgs as a function to the mass all lie along a line. Any deviation from this line is a deviation from the standard model where the Higgs is responsible for the mass generation of all the standard model particles. So, this is the present status. They all align very well. However, look, I mean, again, error bars are huge. Fermion vector couplings is another way to look at the same. I mean, there again, in good agreement, there is always a solution that is compatible with 1-1, where all coupling to Fermion and vector bosons are standard model-like. But again, the regions as the 95% of this level is very large. I mean, you are 50% that you can deviate. I mean, this is interesting because if you take a Higgs signal strength and you compare to a theory where you can predict the deviations, and you take, for example, supersymmetry, you might have learned that I'm an aficionado of supersymmetry, or at least, I mean, it's a theory where you can have some predictivity, and you ask yourself, well, how much can these values scatter in supersymmetry? And you see, I mean, this is a region of parameter space that supersymmetry covers, and you see that I mean, this region is quite comparable to the scattering between the two experiments. It's quite comparable with the error bars. So while you say that all these numbers are standard model-like, they are also SUSY-like, because as the current accuracy, the error bars covers standard model, but covers also the bulk of beyond the standard model physics, like supersymmetry. Run 2 will bring most of this accuracy, just a little bit above 10%. I mean, this is a CMS projection. I mean, this is the Atlas projection. The etched piece here is what comes from theory uncertainty. So you see that will be as a level in which theory and experimental uncertainty will be comparable, at least for some of the couplings. This is a time in which theory must come to the rescue, because then any further improvement from the experiment is wasted, because then it becomes systematically dominated. If you go to the full program, I mean at 3 autobahn of high gloomy LHC, you see that you have again significant improvement, except where you are systematically dominated. But basically, you have everything that will be, let's say, 10%-ish or better. So that will be actually the current measurements are more 20-50%-ish. So that you will have very significant improvement. So if you project that at 300 femtobarn, 3000 femtobarn, the line that I was showing you before here gets now populated by points with much smaller error bars. You're testing basically all these points now to the level of 10%. This will be a very meaningful test. So this is what Run 2 brings you. Run 3 brings you this test that just started to become really probing new physics. How probing they are? My last 2 minutes, 3 slides. So the question is, how does the sensitivity to new physics, to new high mass scales, which comes from the indirect processes probed by precision measurement, for example, in the Higgs sector, compare with a direct probe when you go out and look for new physics just as such. And here I'm trying to show you in 3 different cases. This is the first case, is the CPO, the heavy Higgs mass in supersymmetry. At the moment, I mean now here, the direct searches are not actually constraining this mass for when you take all possible parameters. You always have solutions where the particle might have escaped the search. While if you take the X branching, the X signal strengths, they tell you that this mass must be larger than about 350 GeV, otherwise you'll have deviations from the signal strength of the X measure larger than what is. Already with 50 femtobarn, I mean the direct detection and the indirect will be about the same order, about, let's say, 500 GeV. And then as you increase the sample, I mean this will go out and probe almost to 2 TeV when the indirect sensitivity saturates, because then the particle becomes very heavy and fully decoupled from your theory. But then if you take again supersymmetry, but ask another question, you say, if I take my strongly interacting particles, which actually enter in loops in the determination of the Higgs couplings. And here the situation is different, because depending on the parameters, you already now you are exploring scales of about 1 TeV, when I mean your direct detection explores scale of about 500 GeV. And as you go through, you'll see that at the end of Run 2 and 3, you'll have about 1.5 TeV explored by direct searches, maybe 2 TeV. But I mean, you'll have sensitivity to almost 4 TeV coming out from corrections of your Higgs couplings. And at high gloomy LHC, you go up to 5 TeV. If you go and go out of supersymmetry, something similar. If you look, if you say the Higgs is not a fundamental particle, but is a composite particle, and you look to the mass of your composite mass scale, and then, I mean, you have some sensitivity from direct searches, probably up to something like 2 TeV. But I mean, when you look to the deviation that this compositeness will bring to your Higgs couplings, you're able to probe the scale already now with a scale of about 5 or 6 TeV. So there is a lot of interplay. And you know, once you put everything together, you can test through the LHC as of today, 14 TeV and higher luminosity LHC. You can probe basically, today we are probing something about 30% of your parameter space of a supersymmetric model that goes up to 5 TeV, and we'll go up and we'll probe something like 92% of it. We'll be probing a little bit more when you put dark matter direct detection data. So it's only the interplay of the two, and only, you see that, I mean, you probe 70-80% through direct detection, but you probe more when you put the indirect precision measurements in. Okay. Wrapping up, so the LHC Run 2 is starting. It opens up a decade of data taking, of machine operation, measurement, theoretical ideas studies which are likely to reshape our view of standard model physics beyond the standard model, or at least I hope. The direct searches and the precision measurement in the Higgs and the quark sector promise to be highly complementary in the sense that, I mean, the connection to cosmology through dark matter will be an exciting highlight for the result interpretation, and we'll need to keep direct detection, direct searches and precision measurements in view when we want to probe theory. The results from the LHC depend also on the theoretical and phenomenological input, and that's really important. And so only a tight connection of the theory and the experimental community will actually bring the possibility to fully exploit the LHC potential that we have at hand. Thanks for your attention. Well, yes, there are scenarios. Already, I mean, the R&D that has been put in place for the high energy, for the high luminosity, has been essentially trying to make magnets which has higher gradient, higher field than those which are currently installed. For example, if you'd be able to replace 1/3 of the magnets that are actually in the tunnel with the magnets with a field which is now available for the high gloomy LHC quadrupoles, you'll be able to reach probably 18 to 19 TV. So that's something. And that's what I was saying, that this program is dynamic. It'll depend what you see, but these options are certainly open.
Yeah, Marco, so you haven't mentioned at all the measured value of the Higgs mass, which is totalizingly close to this metastability value for the Higgs vacuum. Should we take this as a serious indication about UV physics? And is it in conflict with the concept of supersymmetry? Maybe this is too long a question, but what's your opinion on that?
It's true. I mean, I didn't, you have seen that already. Next year I will get 1.5 hours. No, well, I mean, the Higgs is light, and supersymmetry predicted it to be light. If you take supersymmetry at random, you get about maybe 10% of your supersymmetric solution, random supersymmetric solution, fall in the prediction of the, in the range, the prediction fall in the range of the current measurement. We shall not take, I mean, as a sign that, I mean, some very specific, highly constrained models are certainly in trouble in explaining. But if you take, I mean, generic MSSM, even more NMSSM, I mean, there isn't a sign that you have really to push your parameter to explain the mass. Certainly, what happens is that you highlight a very specific region of your parameter space. That for sure. But this can be seen as an advantage in the sense that we gain some, especially in the stop sector, we gain some understanding where we have to concentrate our probe.
Okay, one last question perhaps. Thank Marco for a great presentation.
Thanks.